Hello, welcome to ISAT431, Advanced Manufacturing Processes and Systems. This is lecture 5, Nanomanufacturing, the first lecture of nanomanufacturing. So today, basically, we're going to give a little bit introduction about what is nanomanufacturing. Then we'll talk a little bit about the properties of nanostructures as well as how to grow nanostructures. And when we're talking about the nanoscale, we really need to take a look at how the nanoscale compared to our normal scales. Starting from maybe the diameter of the sun, which is the 1 million kilometers, well compared to our human errors, which is around 1 centimeters, until we get into 1 millimeter. That you can see that's very, very small. Well, beneath 1 millimeter, we can see how there are also different scales. So one ant that is about 5 millimeters, well, at a human hair that is about 10 to 50 microns. Well, 1 nanometer that is a thousandth of a micron. So which means it is about several atoms of the length. So when we're talking about nanometer, well, we can think about when we add several atoms. Sometimes maybe that is only one atom, depends on the size of the atom. So that's about that size. And so from this graph, you can see, at a certain length of the scale, how many atoms can be accumulated there. So remember, 1 micron, that is 1,000 nanometers, right? So which means that 100 micron, which is 1/10 of a micron. You can see there may be here we can 10 to the power of 7 number of atoms, so that within this very small scale or small length, actually there can be a lot of atoms. And because of their the large number of atoms, and all these atoms can be actually form different structures. So we learn about crystalline structures or some other structures in ISAT430. We know that all these structures actually form the mechanical properties of materials. So what we're going to do in the nanomanufacturing is we're going to start to manipulate all these atoms into different structures, or we call it building blocks. And using those kind of structures or building blocks, we start to form repeatable patterns of the material. Then when we add it up into a lot of those repeated patterns, then we'll start to scale up into a size that is our normal scale. Then we can create materials that is extraordinary properties compared to traditional materials. So this is how the nanomanufacturing works. And so when we look at the nanomanufacturing, this is really a bottom-up process. So compared to traditional materials, where our traditional product we are making, for example, the left picture, that is a typical machining process. We have a whole block of metal, and then in order to create certain geometry of the metal, we can remove materials by drilling a holes or do some milling of the surface or the sides, and that is a top-down process. Well, the bottom-up process, one bottom-up process we look at it is the additive manufacturing, right? So in additive manufacturing, we only put materials or process material where that is needed. Well, nanomanufacturing is even more bottom up, which means that we are actually starting to manipulate all these the properties starting from the building of the very basic structures from molecules. So we put several molecules together to form a certain pattern, and then repeat those patterns and create the materials. So this is how nanomanufacturing starts, which is a very bottom up process. And this is the video about applications about manufacturing. We can take a look at this.
Today, the use of nanotechnology has been put to practical use for a wide range of applications, including stain-resistant clothes, lighter and stronger automobile bumpers, enhanced computer screens, higher strength metal cutting tools, scratch-resistant coatings, and clear sunscreens. Though these advances have impacted our daily lives, many leading researchers and developers worldwide agree that it's the wide-reaching effects of nanomanufacturing that will usher in the next industrial revolution and replace our entire manufacturing base with a new, precise, less expensive, and more flexible way of making products. Yet the future of nanomanufacturing depends, first and foremost, on creating the tools, instruments, metrological devices, and modeling applications that can effectively build complex structures with atomically precise control. Nanomanufacturing, also known as molecular nanotechnology, is the process of assembling complex structures with atomic precision. The idea is to precisely place every atom within a product so that components are exactly the same size, type, and number of atoms. Nanomanufacturing can be divided into two approaches: top-down fabrication and bottom-up assembly.
All right, so now let's take a look at about basic building blocks of nanomanufacturing. Several building blocks can be created. Let's start from 0 dimensions. We can have a cluster of atoms. So a lot of times we can use some magic numbers to create those structures, and that is a nano cluster. And also nano particles. So nanoparticles will be around hundreds and thousands of atoms, and it form a certain particle that is around 1 to 100 nanometers. And a one-dimensional feature, we can see nano particles or nano atoms can actually form a nanowires. So which means in a nanowire, so all the atoms will start to form a certain shape, like a wire. Well, compared to nanowire, the difference between nanowire versus the nano tubes is that nanotube is hollow. So you can see the difference between the two. And nanotubes, it start from having a sheet, and then have a sheet of nanoparticles, nanoatoms. Then we'll start to fold the sheet into with different rotation angles, and then we'll create different types of nanotubes. So another type of nanostructure is when we are looking at a 2D, that will be nano sheets. So all these nanoparticles can start to form a 2D structure, with x and y axes. Then we'll create the nano sheets. Well, with nanowire, nanotube, so basically that's a line, right? And here you can see the Young's modulus about for example, nano carbon tubes, and starting to look at the foams, where the foams are. Then we have polymers, metals, alloys, steels, and here we have some innovative materials. For example, carbon fibers. Those are here, and then carbon nanotubes. Carbon nanotubes, we can see it really have high strength compared to traditional materials. And about the manufacturing of nanotubes, actually there are a lot of challenges when we are getting into very small scale. But at the larger scale, now it's actually commercialized. Because for those components, we can make them from a top-down process, like remove a material from a building block. Well, if you want to start with making of those very small scale, for example, less than 1 kilogram of the especially electrical components, will have to start to make those carbon nanotubes by making 1 nanotube at a time. So which means that it has a lot of challenges and requires a lot of techniques in order to make those. So that's why current manufacturing technology has certain limitations in making very small components of electrical components with nanomaterials. And when we are looking at the carbon nanotubes, there are really typically two kinds of the carbon nanotubes. One is a single wall. You can see it, a single wall carbon nanotube, and also versus multi-wall carbon nanotubes. So multi-wall carbon nanotube means there, within one tube, there are actually multiple tubes inside it. And the single wall carbon nanotube is about 0.4 to 3 nanometers, while the multi-wall is about 3 to 100 nanometers. Well, from here you can see this is a nano sheet, and so nanotubes actually can be formed in different ways depending how do you fold it. You can see from here we got this region of nano pattern, and if we fold it this way, we got a zigzag shape of the carbon nanotube. And if we fold this part, then we'll get a carol shape of the carbon nanotube. And if we fold this way, this shape, right, fold this shape, and we can get an armchair carbon nanotube. And something to note is that here you can see the different shapes of the. So this is a zigzag, and this is the armchair, and this is carol carbon nanotube. So depends on the length, the angle, as well as some other vectors. So the carbon nanotubes actually can be formed with different properties, and also different different shapes. So in this way, people actually created a periodic table of carbon nanotubes, and the scientists can actually use this periodic table to guide their creation of carbon nanotubes. And here you can take a look at a video about nanoforest, and how you can see how material actually formed from carbon nanotubes perform in our real life.
Scientists like Ray Bachman at the University of Texas are exploring the remarkable properties of a brand new material, the carbon nanotube.
Dave, this is one type of carbon nanotube.
This is what it's all about right here.
This is what it's all about.
I had a hunch it'd be like this. I just thought they'd be smaller. I'm right. They're about 1 billion times smaller. Nanotubes are made of carbon atoms arranged in a rolled-up chicken wire-like structure. Besides nanotubes, there are other forms of pure carbon, like diamond, and graphite, the stuff of pencil lead. Nanotubes get their strength from the extremely strong bonds between carbon atoms.
These carbon nanotubes can have spectacular mechanical properties, spectacular strength, and very high toughness.
And you make them here in this very lab?
Yes, we do.
Ah, so this is where it all happens.
This is where the process begins.
And guess what? It's not even that difficult. Here's all you need. 1. A smooth surface with a thin layer of catalyst, a chemical that helps jumpstart the tubes. 2. A special mix of gases full of carbon atoms. And 3. This furnace, which, by the way, is really, really hot. How much heat is it in there?
Right now it's around 800 Celsius.
That's about 1,500 degrees Fahrenheit.
Wow.
I could nuke a pizza in like 5 seconds in there.
Yeah. You can open more.
Oh man,
See that?
that is
And then it's-
blasting heat. Oh, I see the little black wafer in there. That's it?
Yep.
That's nanotubes?
Yeah, exactly.
Wow, that is very cool. Baking away in there. Wow, it's like a nuclear tanning bed. After just a few hours, the wafer is covered with a thick black fuzz. So it looks just like a piece of black velvet. So if I were to really look in close to that, what would I see? What's it really look like under the microscope?
Well, we call this array of carbon nanotubes a nanotube forest.
The name is apt. Each nanotube looks like a tall, thin bamboo tree, hollow inside. So thin that if you could scale one up until it was 1 inch wide at the base, the top of it would reach 2 miles into the sky. Now picture nanotubes by the billions, all standing shoulder to shoulder, and you have one of Ray's nanotube forests.
There are, in fact, about 200 billion of the carbon nanotubes in that area.
Hold on 1 second, I'm going to count them. Actually, I shouldn't be touching these. Scientists don't yet know if they're toxic. Even so, there's already a rapidly growing market for nanotube particles as strength additives for tennis rackets, bicycle frames, even high-end car bumpers. Many products already incorporate carbon fibers, which are part carbon, part plastic. But nanotubes have greater tensile strength and toughness. Ray has set his sights on making super strong materials that are 100% pure nanotube, made from his nanotube forests.
These aren't just ordinary carbon nanotube forests. They are nanotube forests that have a very special type of connectivity between nanotubes. When we pull out one nanotube, that nanotube pulls out its neighbors, who pulls out other neighbors to self-assemble a yarn or a sheet.
Expert nano yarn spinner Kai Lewis gives me a hands-on lesson.
Would you like to try?
This I recognize. This is that. First, we start with a forest on a wafer.
So you can just grab on to this little orange tab.
Okay.
Now don't make it too high of an angle and make
Okay.
sure it doesn't touch the edge. And just pull out,
Fast or slow?
whichever you feel comfortable with.
Oh, dude. As I pull on this little tab, nanotubes are coming off the wafer, hooking other nanotubes and pulling them off the slide.
Try faster.
I'm so good at this.
And at too high of an angle, it will, as this is now, it'll start to break off from the forest.
It's like coming out forever. I'll see you at the Texas County line. It's still going. It's still going.
There, it broke. And what's even neater, I can show you right here. I can even do a little twist
Oh,
and
you're making
make that into a yarn right here.
Insta yarn.
Look at that.
Wow.
It's about 1/100th of a human hair.
Oh my gosh, it is like steel. I'm pulling really hard. You probably can't even see that. In fact,
And it
look
will
at
stay.
this. It's so fine, you can't even see. Oh, that helps.
Keep twisting. Keep twisting.
Keep twisting. Okay. It's amazing.
It's stronger than steel.
Stronger than steel? So why then don't you take a bunch of these, twist them together, and make this super cable that'll be like bridge suspension cables and aircraft carrier cables?
Can you imagine spinning a bunch of these all day long to make into a rope that's a foot in
All right, so
diameter?
go the other way. Make the aircraft carriers really, really small.
Alright, so from that video, you can actually get some visual understanding about how they look like and how strong it is. And something to note is that, like our normal materials, nanocarbon tubes, they also have some defects. So here's a picture of exposure. Picture you can see, from 0 seconds to 10 seconds, under a certain pressure, and how the nanotubes actually start to form a little bit of defect. see here compares to here, and so it also happens under force, under pressure. But when we're looking at many nanotubes from forest or even bigger structure, and it's like starting off structure from one little wood stick, right? You can easily break it, but once you have a lot of wood sticks, and it's hard to bend and break. So similar to the nanotubes. And so in order to make those structures, one thing we need to do is we need to see it, right? Because they're really at a very small scale, and our traditional optical microscope actually have limitations. So you can see typically our optical microscope is about one micron, and the magnifying power will be around usually it's 10 times 1,000 times of the magnifying power. But when we are looking at a nano scale, we're really looking at is the 10 to the power of -9 the scale. So how do we reach that? Then we'll have to think about either developing other methodologies or techniques in order to see them, or we find a way traditional optical method, but giving more magnifying power. So this is a traditional optical microscope, as you can see the setup. So here we get a limehouse, and then start to emit the light. Here is a mirror, and then the mirror will reflect the light and go through the specimen. Here is a specimen, and then here up here we got a detector. We can visually see the specimen by having the light go through the specimen, because the specimen is very, very thin. So this is our the principle, our traditional optical microscope. But there are a lot of limitations because of diffraction. Light diffraction. So light diffraction means when you are giving the light, actually goes through the specimen. Actually diffraction will happen, and it will reduce the power of the or reduce the energy of the light. So which means to form some places can be a little bit strong, some places can be a little bit weak. So which means that the image will have a very poor blur image from what we see. So this is how it limits our the resolution of the optical microscope. For the optical microscope, some scientists actually start to create different methods to think about how we can make a better resolution of those images. And one method is fluorescence. Use fluorescence to reconstruct the image of object. What happens is it will start to give fluorescence to the specimen, and some of the materials, some of the structure that we're interested in will be highlighted through the light. And then by giving the light through those the images through the specimen, actually the specimen will start to, especially the places with fluorescence, actually will start to emit the light with different waves. So using by detecting those kind of waves, we're gonna repeat this process by giving the light every second. So it will start to accumulate a lot of images, or accumulate a lot of light spots with different images. And after we get enough number of those images, we can actually reconstruct those image of the object by having all these resources. So, and people have developed different methods like 2D storm and also 3D storm. So the method of using fluorescence to reconstruct the image of the object, it actually received the 2014 chemistry Nobel Prize for how categorizing the the structures and also the materials at a nanoscale, especially applied into mathematical areas. Well, another group of technologies actually use different method. They are not using optical method. They are actually using electron methods. So electron method means we'll start to give a beam of electrons from the electron gun, and then we'll shoot the electrons to the specimen. You can see it's located here, and when the electron shoots the specimen will actually start to emit the electrons, and all these electrons can be detected here, and by detecting all those emitted electrons, we can construct the images. All right, construct images here on the screen. So this is how we can use scanning electrons to create a method or create the equipment to see even smaller scales, at the nanoscales. So this is called scanning electron microscope. It's called SEM. We can take a look at this video, see how what this equipment looks like.
By now you've had some experience using the small electron microscope, the TM1000. Now we're going to add some theory behind what's actually happening inside the electron microscope. And I actually delayed this until now, until you had a chance to use the small electron microscope, because hopefully it'll help it make a little bit more sense to you. So here's a cutaway of what the inside of our electron microscopes look like. This is not exactly ours, but it's going to be very similar inside. Essentially what we have is we have an electron gun up here, which we're going to induce to send a beam of electrons down to our specimen down here in the chamber. And to focus that specimen, we'll be using a series of electromagnets. Now, we can't use glass lenses like you find on a regular microscope because the electron beam won't go through glass. But the electrons have a charge, which means that they're influenced by magnetic fields. So these rings right here, these condenser lenses, if you will, are actually just electromagnets. And the idea is to get those electrons finally focused right down here on the sample. So first of all, let's take a look at the electron gun. Electron gun, here's a photograph taken with the Leica dissecting microscope. This is called a thermionic electron gun, which basically means we're going to heat it up. It's going to give off a bunch of electrons. To give you some idea of the scale here, this is just a penny I had in my pocket. I stuck down there with it so you could see what's going on. By the way, just to show you a nice image from the Leica here, you can see that this filament's actually burned out. So this wears away as we use it. We put that 15,000 volts through there, or on the big scope we'll put up to 30,000 volts through this filament, and it eventually burns away. All right, so let's go back and look at our cutaway again. So the way we get these electrons to head down toward the specimen is the fact that under this you'll see a disc called an anode, and anodes have a positive charge, and of course negatively charged electrons are going to be attracted to our positively charged anode, so they head off in that direction. But there's a hole right in the middle of the anode, so once these guys start moving toward the anode, some of them will simply go right through it. Also, the stage down here on which you're going to mount your specimen also has a positive charge, so that also keeps the electrons moving in this direction. This can cause us a problem. A lot of things we look at in our microscopes are non-conductive. And as you found out hopefully with the TM1000, if you have something that's non-conductive, it can actually gather a charge, and then it gives off lots of electrons, and all we see is a glow. So let's take a look at what happens when the electron beam hits the specimen and how that ends up making an image on our computer screen. So here you can see the electron beam heading down. It hits the specimen here, and then there's actually two types of electrons that are going to come off of this. In one case, we're going to get the what are known as secondary electrons, and that is when the electron beam comes down and hits the atoms of the specimen, those atoms absorb the energy and give off their own electron. There's a detector to pick up secondary electrons over here, as you can see, and that detector to attract those electrons has a positive charge on it. It's about 300 volts, which is actually quite a lot. And then once those electrons come in to the Faraday cage, which is positively charged, they hit the detector. And then the detector uses the information from those electrons to form the image on our computer screen. Now, the second type of electrons are called backscatter electrons. And these electrons actually don't come from the atoms. They actually reflect off the surface. And they actually can come even from deeper down in the specimen. And we have a second detector that can actually detect those. So this is to show you, this illustration will actually show you where these electrons are going to come from. So you can see here the secondary electrons are going to be surface electrons. So they're very shallow, but these are very, very good for getting surface features. And of course, that's one of the main reasons for using a scanning electron microscope. The backscatter electrons are going to come from deeper in the specimen. So some of them will bounce right off the surface, some will go deeper. And then the ones that are really deep actually never get back out again. So when they get absorbed, they give off X-rays. Now, we actually don't have an X-ray detector for our scope, but you can do elemental analysis by looking at X-rays. So the detectors that we have on our scope are the secondary electron detectors and the backscatter detectors. So why is it called a scanning electron microscope? Well, as you can see from this illustration, here's our primary beam coming down, and it's actually making the picture pixel by pixel. It's hitting from left to right, top to bottom, and every time it hits, we get electrons from that particular part of the specimen. Interestingly enough, if you want to magnify, all we do instead of actually scanning across a big image like this, so we just would scan over a smaller box. So this is actually showing the setup. As you can see here, we've got the column here, so all the electromagnets are up above there. The electrons come out through the pole piece here. They hit our specimen. The secondary electrons over here to the side, and then of course our backscatter detector is actually going to be up here mounted to the pole piece. And you saw a picture of that inside of the TM1000.
All right, so that's a little bit another explanation of SEM. Another method for using electrons is called transmission electron microscope. So transmission electroscope, or TEM, uses the method of also start with a source of electrons, but the difference is that the electrons are actually going to go through the specimen, and then the emitting electrons will be go through the two lenses and then start to form an image here. So this is how the transmission electron microscope works. Well, compared to the SEM, you can see the the electron actually in the SEM didn't really go through it. Instead, it just reflected. So here is a comparison between SEM versus TEM. TEM actually has a higher resolution compared to SEM. You can see the resolution can be here 10 nanometers and 0.5 nanometers in some special cases. In SEM, it has lower resolution, and magnifying power. Actually, you can see TEM has a much bigger magnifying power compared to SEM and also traditional microscopes. And this is a figure or image difference between the SEM versus the TEM. As you can tell, that TEM actually can see very individual atoms from the image. Another method is the atomic force microscope. So the method of this is very similar actually to one of the methods when we are looking at the surface finish, right? So which is to use a tip. So the tip is actually composed of some atoms, a group of atoms, and then by moving the tip across the surface of the specimen, right? It can actually because of the tip gonna move up and down. So you can see this gonna move up and down. So we use a laser to by reflecting the laser beam, we can actually tell the distance of the light traveling to create the image. from this photodiode, and then we'll start to create the image of the specimen. So this is the method of using AFM. We can take a picture. We can take a look at this video.
An AFM is an atomic force microscope. It lets you see things that are very, very small, all the way down to the nanoscale. How does an AFM work? An AFM uses a cantilever with a very sharp tip to scan over a sample surface. As the tip approaches the surface, the close-range attractive forces between the surface and the tip cause the cantilever to bend towards the surface. However, as the cantilever is brought even closer to the surface, increasingly repulsive forces cause the cantilever to bend away from the surface. An AFM has a Z scanner that moves the cantilever up and down, an XY scanner that moves the sample back and forth underneath the cantilever, and a position detector that records the bending of the cantilever. The position sensor works by tracking a laser beam that is reflected off the flat top of the cantilever. Any bending in the cantilever will cause changes in the direction of the reflected beam. The position detector then tracks and records those beam changes. Using the detection method explained earlier, an AFM images the topography of a sample surface by scanning the cantilever over a region of interest. The raised and lowered features on the sample surface influence the bending of the cantilever measured by the position detector. AFM generates an accurate topographic map of the surface by using a feedback loop to control the height of the tip above the surface. There are two major methods of AFM imaging: contact AFM and non-contact AFM. In contact AFM, the cantilever scans across a sample with its tip touching the sample surface. Because the tip is in contact with the surface, strong repulsive forces cause the cantilever to bend as it passes over the surface features. The advantage of this method is the relative simplicity of its technology. However, there are disadvantages. One disadvantage is that the sample can be damaged by the gouging action of the sharp tip. Another disadvantage is that while the tip is gouging away at the surface, it also grinds down the tip, which reduces the quality of your image. In non-contact AFM, the cantilever oscillates just above the surface while it scans, but the tip does not touch the surface. A precise high-speed feedback loop is used to keep the cantilever tip from crashing into the surface, thus retaining tip sharpness and leaving the surface untouched. As the tip approaches the surface, interactions between the tip and the surface cause the oscillation amplitude of the cantilever to decrease. The feedback loop corrects for these amplitude deviations and constructs an image of the surface topography. Non-contact AFM has many advantages over contact AFM. It preserves your sample surface because the tip and surface are not touching. By prolonging the sharpness and lifetime of the tip, it allows for high-quality imaging over many scans. This also brings down the total operating cost of the instrument, as tips are expensive to replace. Atomic Force Microscope, or AFM, is a powerful tool that enables you to see, explore, and obtain measurement data from your samples at the nanoscale. For more information, please visit parkafm.com.
All right, another video about AFM. You see some. So the tape actually goes through the surface. All right. Next, let's look at the energy carriers of the nano manufacturing. So where all these energy resided. So in ISAT430, we'll talk about the electrons and how how these atoms at first form or molecules form crystalline structures. There are different bondings, right? Those in the bonding actually form a very basic energy source from electrons. So that is called either ionic bonding or covalent bonding, and those kind of interaction between electrons actually is one source of the power or energy. Another source of power of energy is photon, which is a quantum of the electromagnetic field, and which is the basic unit, also the basic unit of light. It carries the energy itself. Also, there's one is it's called phonon, so which is quantize the mode of vibration of the lattice. So in the lattice structure actually has vibrations. So during the vibration, we'll start to create emit some of the waves. Those kind of waves actually also going to have energy carry in it. Another one is exciton. So exciton is quasi-particle, so it's a bound state consisting of an electron and also a hole, as you can see from here. So it's more of a formation. So the formation is actually net zero charge, which means it does not have positive or negative charge that can interact with other electrons or other things. But the formation itself carries the energy, and by moving those excitons, actually the energy will be transferred from one state to another. So interconnections of atoms, so it's more form like the spring system. You can see, so atoms between atoms, they also have electrons, and then all these electrons start to form a bonding, and those bondings will actually start to form the basic structures of nanostructures. So those springs actually have a very strong formation or strong strengths, and that's why you can tell how the nano carbon fibers actually have a strong Young's modulus compared to traditional materials, because traditional material only have that typical structure, either crystalline structures or some other structures. But nanofibers actually we start to manipulate different shapes, and then those structures have even higher bonding than crystalline structures. And here you can see a nanotube array, and when there's no force pressing on it or stretching it, it has a free length. And when there is a compression force, it operates as a spring system. And once the force released, it will also release recover its original length. So having this spring system with the carbon with nanotubes, actually we can create like we watched in the video, a whole forest of the materials. And as you can see, from this image, this is only 12 microns of carbon nanotubes. So this is a stress strain comparison. Next is the wetting. So wetting means wetting is actually the ability of a liquid to maintain contact with a solid surface, resulting into intermolecular interactions. When the liquid and the solid are brought together. So in other words, the wetting means the ability to keep its original shape. When you have a liquid and also solid interface. So wetting is really determined by a balance between the adhesive and also cohesive forces. And liquids, more frequently wet, solids having when solids have really high surface energy. So what it means is if the surface, if the solid here has really high surface energy, which means liquid will have more of the wetting compared to some other solid surface materials. In this case, what we're going to do is we can actually use nanotechnology to create the solid surface on the materials, and then to create some of the the more of the wetting features for those materials. For example, waterproof, right? So when water gets on the material, it actually will keep this wetting, and then this is how the water will be proofed. And here is a video. Let's take a look at this.
In previous sections, we have learnt that water spreads on hydrophilic surfaces and beads on hydrophobic surfaces. We defined ideal surfaces as well as the contact angle of water, and said that contact angles were a measure of spreading or beading of water on a surface. Here is a mind map of the topics we will cover in this section. Let's begin by looking at Young's equation. To calculate the contact angle of water on an ideal surface, we use Young's equation. The equation uses the interfacial free energy values of the solid-liquid, solid-gas, and liquid-gas interfaces to calculate contact angle. Interfacial free energy, also known as surface or interfacial tension, is a measure of the energy required to create a unit area of the interface measured in joules per meter squared. The interfacial tension can equivalently be considered as a force acting on a line of unit length of the interface measured in newtons per meter. For a droplet of water, the molecules at the surface have fewer nearest neighbours than those in the bulk. As a result, the intermolecular attractions between the molecules at the surface is greater, creating a surface film of stronger interactions. This is called the surface tension, as the surface is bound more strongly and is harder to penetrate than the bulk of the droplet. This is why objects denser than water can sometimes float on a surface. A useful analogy is that the force or surface tension that holds a water droplet together is like the elastic skin of a balloon. When the surface tension is penetrated, the droplet will disperse and the water will spread. Young's equation arises from considering the condition of thermodynamic equilibrium, where the three interfacial tensions, treated as forces, are balanced in the horizontal direction along the line of the solid interface. Rearranging the equation, we can obtain the cosine of the contact angle in terms of the interfacial tensions. The value of the contact angle can be between 0 and 180 degrees and varies widely depending upon the chemical compositions of the solid, liquid and gas that form the interfaces. The interfacial tension of the solid surface is key to determining whether a surface is hydrophilic or hydrophobic. Historically, a contact angle of 90 degrees has been the cutoff point between hydrophilic and hydrophobic surfaces. When the contact angle is less than 90, cosine theta is positive. From this, we can assert that the solid-gas surface free energy is high for hydrophilic surfaces. When the contact angle is greater than 90, cosine theta is negative. Similarly, we can say that hydrophobic surfaces have a low solid-gas surface free energy. In reality, no surface can be perfectly ideal, and it is the imperfections of the surfaces, such as topography and roughness, as well as the chemical composition, which determine how water droplets will behave. For non-ideal surfaces, Young's equation must be modified. We now need to consider the contact angle hysteresis, which is taken to be 0 in the ideal case. Contact angle hysteresis is the difference between advancing and receding contact angles. The advancing contact angle is the maximum stable contact angle, whilst the receding contact angle is the minimum stable contact angle of a water droplet. By tilting a droplet, we can easily visualize the difference between the advancing and receding contact angles. One method of measuring contact angle hysteresis is by using the Cecil drop machine. The machine films a water droplet on a surface side-on using a high-speed camera. The volume of the drop is then varied using a needle. The advancing contact angle is measured after increasing the volume of the drop, whilst the receding contact angle is measured after decreasing the volume of the drop. These angles and the difference between them vary widely depending on the surface. When looking at how a water droplet lies on a non-ideal surface, there are two different regimes to consider. In the Wenzel regime, all of the liquid droplet is in contact with the surface. The apparent observed contact angle is different to that measured by Young's equation because of the roughness of the surface. The apparent contact angle for a Wenzel state is related to Young's contact angle by the given relation. In the equation, R is the surface roughness, which is a ratio of the true surface area over the ideal flat surface area of the solid. R is always greater than 1 because of the surface roughness. As a result, the magnitude of the cosine of the apparent Wenzel angle is always greater than the cosine of Young's angle. Because of the relation between the magnitudes of the two cosines, it can be shown that when Young's angle is less than 90 degrees, the Wenzel angle is less than Young's angle. This shows that hydrophilicity is increased in the Wenzel state relative to the ideal case. When Young's angle is greater than 90 degrees, the Wenzel angle is greater than Young's angle. This shows that hydrophobicity is also increased in the Wenzel regime compared to the ideal. We have shown that by increasing the roughness of the surface, going from the ideal to the non-ideal Wenzel case, hydrophilic surfaces become more hydrophilic, and hydrophobic surfaces become more hydrophobic. Droplets in a Wenzel state demonstrate high contact angle hysteresis. This is because the droplet is in contact with the surface at all points, which leads to high adhesion as there are lots of interactions between the droplet and the surface. Wenzel surfaces also have a high roll-off angle. The roll-off angle is the angle a flat surface needs to be tilted before a water droplet sitting on the surface will roll off spontaneously. Wenzel surfaces often display microscale roughness, but not enough roughness for pockets of air to become trapped between the surface and the droplet. This is the case for droplets in the Cassie-Baxter regime. In the Cassie-Baxter regime, not all of the liquid droplet is in contact with the rough surface. Cassie-Baxter surfaces usually have increased roughness compared to Wenzel surfaces. There are pockets of air between the lower parts of the solid surface and the droplet. The droplet is effectively sat upon a composite surface made up of the highest parts of the solid surface and air pockets. Here we see the surface of a lotus leaf, which is comprised of tall pillars. We can easily see how a droplet could sit on these raised parts, analogous to lying on a bed of nails. The apparent contact angle is modified further from Young's equation in the Cassie-Baxter regime. Here, F denotes the fraction of the solid surface which is in contact with the liquid, i.e. the fraction of the solid that is wet, and RF is the roughness ratio of the wet area. In most cases, the Cassie-Baxter equation predicts a higher apparent contact angle relative to the Young angle. This is different to the Wenzel equation, where the apparent angle is higher only when Young's angle is greater than 90 degrees. Droplets in the Cassie-Baxter regime show low contact angle hysteresis. As the droplet is only in contact with the surface for a fraction of the area, the adhesion between the solid and liquid is reduced greatly. As a result, Cassie-Baxter droplets tend to have low roll-off angles. In the extreme cases of wetting, we can introduce two new types of surface, the superhydrophilic and superhydrophobic surface. Rough surfaces, where contact angle is very low, less than around 5 to 10 degrees, which often cannot be measured because the amount of spreading is too great, are said to be superhydrophilic. In these cases, complete wetting is said to have occurred. At the other end of the spectrum, rough surfaces with very high contact angles, above 130 to 150 degrees, very low contact angle hysteresis and low roll-off angles are said to be superhydrophobic. Superhydrophobic surfaces are often in the Cassie-Baxter regime. The most vital condition for our definition of superhydrophobicity is a contact angle hysteresis of less than 10 degrees. The low hysteresis leads to a low roll-off angle. Hysteresis is low because of the low adhesion between the surface and water, due to lack of interaction from the rough composite surface. An example of a surface which is naturally hydrophilic is glass. This is because glass has a high interfacial tension of around 1000 millinewtons per meter. The interfacial tension of the water-air interface is much lower, at 73 millinewtons per meter at room temperature. As a result, the contact angle is very low for high-energy surfaces such as glass. The composition of glass, which is made of polar ionic salts such as silicon dioxide, makes interaction with water favourable, and so water spreads. At the surface, the presence of silanol groups means that glass can form hydrogen bonds with water. As a result, water can chemisorb to the surface. Many polymers are naturally hydrophobic. The surfaces of hydrophobic polymers have low interfacial energy values relative to water. Consequently, the contact angle for these surfaces is high. A polymer with a very low interfacial energy of 18 millinewtons per meter is polytetrafluoroethylene, commonly known as PTFE. The structure of the polymer, a carbon backbone surrounded by fluorines, gives rise to strong hydrophobic properties. The fluorine atoms in PTFE are highly electronegative and create extremely strong bonds to carbon, which render the polymer virtually chemically inert. Consequently, the interaction of PTFE with water molecules is unfavourable, so PTFE is hydrophobic. Over the course of this section, we have seen how Young's equation is formed and how it is used to calculate contact angles for ideal surfaces. We have expanded on Young's equation to look at the non-ideal surface cases, studying the Wenzel and Cassie-Baxter regimes. We have also defined contact angle hysteresis and seen how it is measured and termed two new types of surface, superhydrophobic and superhydrophilic. Finally, we have discussed examples of different materials which are hydrophobic and hydrophilic, and explained the origin of their behaviours in terms of surface free energy and interactions with water.
Alright, I think this video gives a very comprehensive introduction about what is wetting and how the wetting works. And you can see all these pictures in the slides. And next, I want to talk a little bit about the production of nanomaterials. There are really two different categories of processes. The one is a physical method, and another one is chemical methods. So I'm gonna go through in several methods in this course. And the first one is a physical method, which is the ball milling. We can use ball milling process actually to break the chains of or break some of the connections from nanostructures. And this is how this is one of the traditional physical methods we can use to form nanostructures from bigger chains to smaller chains. Well, another method is lithography. So this is a very, very, very important process, especially used in microchip processing or making microchips. We know microchips actually are getting smaller and smaller, and making those microchips requires a really complicated process, and the technology actually is dominated by only some large companies. So this is why the companies actually having this technology, as in with even more precise processing parameters, can actually get a lot of market share in the microchip industry. And currently, we know that in worldwide there's a shortage of processing or manufacturing capacity of microchips, and one of the reason is because making all those equipment with lithography is actually it's limited. So that's why. So they're going to look at the lithography. Actually, we already talked a little bit about this process when we were talking about additive manufacturing. The process is similar to that. So first, what I do is we have substrate, we have the target material. So this material is something we need for making the product. And then what I do is when I apply a polymer resist polymer material on top of this, and then when I start to having it exposed to the photo. And what happens is when I put some of the mask materials, which is blocks the photo exposure at certain places. There's a positive resist and also negative resist, so you can create different patterns, on the material. So what happens is, the polymer material actually start to create a different pattern. You can see the patterns here. Then we're gonna have the etching process in order to process our target material. And then next process is remove the resistant material to leave the surface feature. So basically, this is lithography, and for making the equipment of doing this, it actually requires several technologies. For example, the applying of a new layer of materials, having this photo exposure, and then etching, and also removing. That's why the process the equipment becomes a lot complicated. And another process for making nano manufacturing products is by positioning the individual atoms. So positioning the individual atoms, actually we're using cantilever. So and at the tip, it's kind of similar to the to a scanning method when we are trying to categorize the image. So there will be several atoms here, and then because of the force, right? Because force, it will start to attract one single atom, and then by attracting one single atom, with this force, we can actually drag the atom from one position or one place to another. So this is how we can position individual atoms, and you can see some of the pictures scientists have did to create different images or patterns. And let's first take a look at this general method.
In a significant move forward in the march toward creating electronic circuits that are thousands of times smaller than today's most advanced technology, IBM is announcing a milestone in the ability to manipulate and understand matter at the atomic level. Scientists at IBM's Almaden Research Center in San Jose, California, have for the first time demonstrated the ability to measure exactly how much force is needed to move individual atoms. Knowing the different forces required to move different atoms will allow IBM's nano-constructionists to figure out which materials should be used for building devices from the atom up. For example, a so-called sticky atom would be used for something that you don't want to move, like a base that you want to keep in one place, while a so-called slippery atom would be used when you want to build something like an on-off switch that needs to move with ease.
10 or 20 years ago, nobody could imagine that we would have today laptops, cell phones, and iPods. I think it's impossible to speculate what nanoelectronics will bring us in 10 or 20 years, but I'm sure it will change our world even more than the iPods we have today.
The force is measured via tiny changes in the frequency of a small quartz tuning fork. This exploration of the realm of atomic scale structures and devices stands to impact the future direction of information technology. This is Jeff Gluck reporting.
All right, so a little movie actually Stan has made is the boy with his atoms. So another video is about talking about how this movie is made with Stan is how they drop the atoms and created different
we can look up
images.
in the sky and see the stars and nebulas and other galaxies with a telescope and be excited by the strange, interesting patterns the universe forms. And we can also look in the other direction, down towards the small, and see new and strange and exciting patterns that are formed by these pieces of the universe that we're all made out of.
You know, we're trying to make a movie using atoms, and so that sounds like a simple concept, but in reality, of course, these atoms, it does take some concentration because you want to get them in exactly the right spot. We have a tool that allows us to move atoms on surfaces and build structures one atom at a time, and we want to explore how can we use atoms on surfaces to do computation and data storage.
I thought when I first heard that we're gonna make a movie out of atoms, I thought that's crazy. I was worried that it would be a lot of work moving these atoms, and we've started making some of the frames. It's kind of cool, and it's addictive.
All the action of our movie, our little guy made out of atoms, is going to be right on top of one of these surfaces. So to make this animation, we move molecules around one at a time to draw a little picture. And we save that picture and move on to the next frame to start to tell a story.
This is a very challenging task because nobody, as far as we know, including ourselves, has ever moved 5,000 atoms.
Now we see the man that's built with all these carbon monoxide molecules, and then some of them we would have to shovel away to make it really be the movie frame, so we would have to clean up a little bit.
When we see the image in the microscope, we see it magnified about 100 million times. If an atom was the size of an orange, then the orange would be the size of the whole planet Earth.
What we have been doing for the last 40 years is we've taken essentially the same silicon transistor and we scaled it down, putting correspondingly more transistors on the same chip. Very recently, what we have done is we've been interested in the magnetic properties of atoms on surfaces. And really what we wanted to answer is a very simple question. How small can you make a magnet and still use it for data storage?
We know that we can make it stably out of 1 million atoms because that's what's done in current technologies. And we found that for the materials that we chose and that we're able to work with, only 12 atoms is sufficient.
You could carry around not just, 2 movies on your iPhone or something. You could carry around any movie that was ever produced, basically. We're using 2 scanning tunneling microscopes to make this movie. First, we need to look at the surface and we need to figure out where the atoms are. So here we have the atom that we want to move. Here we have our needle. And we switch between the imaging mode, where I stay relatively far away, to the moving mode, where I get close in. And now these 2 atoms are so close that they chemically react with each other. And so then we can drag this atom along the surface and position it to a new location. Here you are actually in the microscope room. This is the room where the actual tip is, where the sample is, where the action is taking place. We're working at a temperature of minus 260 something degrees centigrade. We do this so that these atoms hold still. When we're moving atoms in the laboratory, you'll actually hear a noise.
Now the sound you hear is the sound of the molecule following the tip along the surface.
For us, hearing this scratchy sound is important feedback because we can count how many positions have you actually moved. You go, and you can say, all right, this was 3 locations. Now, of course, we usually build things that can do computation data storage. In this case, we're just telling a very simple story of a boy named Adam falling in love with an atom, dancing together, playing together.
I think it's very exciting to be able to share something that I really love. Maybe it helps other people be fascinated just by the size of atoms.
If I can do this by making a movie and I can get 1,000 kids to join science rather than go into law school, I'd be super happy.
The ability to do something just because you find it interesting is a really important thing, particularly for research, because that's how you stumble across things that are new.
Now, we can't know in detail what those future technologies will be, but we can lay the scientific groundwork for them, and we can spur our own imaginations and get a head start in exploring these new worlds.
All right. So next process is atom layer deposition. So which means that we're actually, every time we put a layer have a layer pause of the layer materials, and then do a purge, to clean the byproduct from it, and then when I repeat this process, time and time and again, and then eventually we're going to create multiple layers on top of the substrate. So this is the coating process. So every time you put a layer on it, then the byproducts will be created, and you have to clean the byproduct, get out of that. Then you can get another layer on top of it. And we can repeat this cycle, n times. Eventually we'll get a structure we need. All right. Another process is to grow the nanotube, the nanowires. So in order to grow nanotube, the nanowires, first we need to have a substrate, which is the source to support all these atoms. And another important component is a catalyst. So the catalyst is the place is a component that it actually helps to grow the atoms. You can see this is how a nanowire actually start to grow, the direction of the growth. And of course, growing of nanotube and nanowires, it takes time. So in next lecture, I'm going to talk about how these structures actually can be made. All right, so that's all for this lecture.